Demonstration problem. If the sign in the picture below weighs 200 pounds and the tension in the left vertical cable is 130 pounds, what must the tension in the right cable be? To answer this question, we need to know that the sign is in equilibrium. Recall that equilibrium means that the velocity is constant. In this case, the velocity is constant of the flavor at rest. We also know that these forces are parallel forces, and therefore they cannot be concurrent forces. They cannot intersect. In our force diagram, we do put the weight at the center of gravity of the sign in this case. The forces that we are interested in are the forces on the sign. The difference is that we do not collapse the sign to a particle at its center of gravity, and we do not put all the tails of all the force vectors at the particle or the center or the origin of our coordinate system. To solve this problem, we apply the first condition of equilibrium for parallel forces. This simply says that the sum of all the up forces is the sum of all the down forces. We go through the problem-solving process. The givens are the magnitude of A is 130 pounds. The weight has a magnitude of 200 pounds. The unknown is what is the magnitude of vector B. The equation is the first condition of equilibrium. The magnitude of all the upward forces summed is equal to the magnitude of all the downward forces. Substitute symbolically first. A plus B, those are the upward forces, is equal to the sum of the downward forces, which is just the weight force. Substituting in numerically, we get 130 pounds for A plus the unknown is B, and we substitute in 200 pounds for the weight vector. We solve and we get B has a magnitude of 70 pounds. Demonstration problem 2. Now you do not know the tension in either of the cables in the bowling sign picture below. The sign is uniformly dense, which means that its center of gravity is in the geometrical center of the sign, and it is 5 feet long. The cable on the left is 18 inches from the left end, and the cable on the right is 15 inches from the right end. What is the tension in each cable? If vectors A and B supporting the sign are equally distant from the center of gravity of the bowling sign, where all the weight appears to be concentrated, this is a very simple problem. It would be the case that both vectors A and B support half of the weight. Let's see if that is the case. The length of the sign is 5 feet. Since the weight is concentrated at the center of gravity of the sign, since it is uniformly dense, no air pockets, no rocks, no holes, that means that the center of gravity or weight vector acts at 2.5 feet from each end. We're given that the left supporting force vector, or A, is 18 inches or 1.5 feet from the left end of the sign. We're also given that the right supporting vector, wire, B, is 15 inches or 1.25 feet from the right end of the sign. This says that since this is 2.5 feet and this is 1.25 feet, that vector B acts at a point that is 1.25 feet from the center of gravity. Vector A, since this is 2.5 feet and this is 1.5 feet, this line of action for vector A is 1 feet from the line of action of the force vector. The line of action is an extension of a line through the force vector indefinitely both ways. So this is the line of action of the weight vector. We see that 1 feet and 1.25 feet are not the same, and therefore we can't simply say that each vector supports half of the weight of the sign. We will have to use the second condition of equilibrium for this, and that involves torque. Recall that torque is a force times a moment arm. Symbolically, the force is just F, and the moment arm is R perpendicular. A torque is a force with a moment arm that has a tendency to cause rotation. Since torque is a force times a moment arm, to understand what torque is, one must understand what a moment arm is. R perpendicular, or the moment arm, is defined to be the perpendicular distance from the axis of rotation, or AOR, to the LOA line of action of the force that has the torque. torque. This definition is true regardless of where you put the axis of rotation, but one must choose the axis of rotation smartly. You should always put the axis of rotation, or AOR, at the point of application of an unknown quantity. Here we have two unknown quantities, the magnitude of vector A and the magnitude of vector B. Therefore, we can pick either one of them. For concreteness, let's put the axis of rotation at the point of application of vector A. You should always, for bookkeeping purposes, circle your axis of rotation and label it. We're now ready to calculate the moment arms for the weight force vector and force vector B. The moment arm for the weight force vector is the perpendicular distance from the axis of rotation, shown here, to the line of action of the force vector, shown here. That is 1 foot. The moment arm for tension vector B is the perpendicular distance from the axis of rotation to the line of action of vector B. That we see to be 1 foot plus 1.25 feet, or 2.25 feet. Now that we know what torque is, we are ready to state the second condition of equilibrium for non-concurrent forces. The sum of the torques clockwise is equal to the sum of the torques that are counterclockwise. Since torque is force times the moment arm, this means that the sum of the forces times their moment arms that act in the clockwise direction is equal to the sum of the forces times the moment arm that act in the counterclockwise direction. Now that we have the necessary information, let's go through the problem-solving process. The givens are the magnitude of the weight force vector is 200 pounds. We have determined that the moment arm for the weight force vector is 1 feet. Remember, that is the perpendicular distance from the axis of rotation to the line of action of the force. In this case, it's the line of action of the weight vector. We also have that the moment arm for force vector B is 2.25 feet. That's the perpendicular distance from the axis of rotation to the line of action of force vector B. And in addition, we have the dimensions which are labeled on the diagram. The unknown, or unknowns in this case. What is the magnitude of the tension in cable A, and what is the magnitude of the tension in cable B? The equation or equations. Since the sign is at rest, it is in equilibrium. These are non-concurrent forces. Therefore, the first condition of equilibrium is that the sum of the forces in the upward direction is the sum of the forces in the downward direction. The second condition of equilibrium says that all torques must be balanced, or the sum of the clockwise torques is the sum of the counterclockwise torques. This holds for any axis of rotation. We have chosen the axis of rotation to be at the point of application of the unknown force A. This will give force A 0 torque, and it will not appear, A will not appear in the second condition of equilibrium condition. Substitute. First of all, first condition, sum of the upward forces is the sum of the downward forces in magnitude. The upward forces are A and B. We don't know the magnitudes of either one of these, so we write A plus B. The only downward force is the weight force. Its magnitude is 200 pounds, so we have A plus B is 200 pounds. That's one equation in two unknowns, so we're stuck. So we must write the second condition of equilibrium. We now write the second condition of equilibrium, or the sum of the clockwise torques is the sum of the counterclockwise torques. This becomes that the sum of the forces times the moment arms for clockwise torques is the sum of the forces times the moment arms for the counterclockwise torques. First, let's deal with the clockwise torques. Consider the axis of rotation, or AOR, and imagine that a pin is nailed into the axis of rotation so that the sign can only rotate about that pin. Notice that the weight force tends to rotate the sign in a clockwise direction about the pin. Therefore, the weight force has a clockwise torque. So we write the magnitude of the weight force times the moment arm of the weight force. Note that in the torque equation, the force is the magnitude of the force times the moment arm. While the weight force is downwards, you only write the magnitude of the weight force. You do not write a negative sign with F sub W. Moving to the counterclockwise torques, again consider a pin driven through the axis of rotation. Then note that force vector B, acting this way upwards, would tend to rotate the sign about the pin in a counterclockwise direction. The only counterclockwise torque is that of force B. We write force B times the moment arm for force B. Now substitute in numerically. The magnitude of the weight force vector is 200 pounds. We have already determined that the moment arm for the weight force vector is 1 foot. In other words, the perpendicular distance from the axis of rotation to the line of action of the weight force, that distance is 1 foot. Moving to the other side of the equation, we write the unknown, or the magnitude of force B, times this moment arm. We found that that was 2.25 feet, or the perpendicular distance from the axis of rotation to the line of action of force B. 1 foot plus 1.25 feet is 2.25 feet. We can now solve for the unknown force B. B is 200 pounds times feet divided by 2.25 feet, which to 4 significant figures, since this is a 3 significant figure problem, is 88.89 pounds. Note that by picking the axis of rotation at the point of application of the unknown force vector A, that A's magnitude did not appear in this equation. Therefore, we could solve for the unknown B in this equation. Our strategy now is to take what we have found for B and to substitute this into the first condition's equation. A plus B is 200 pounds. Then we will solve for the other unknown, A, and the problem will be completed. We proceed to do just that. We substitute in for B 88.89 pounds. And then when we solve for A, we get 111.11 pounds. However, we can only report 3 significant figures accuracy. Finally, for our answers, we get that A is 111 pounds, B is 88.9 pounds. This should not surprise us that A has more tension in it than B, because A is closer to the center of gravity of the sign where all the weight appears to be concentrated than is B.